Alright, so let's talk about electric fields a little bit more. And we're going to start by reviewing a little bit topic 6, and hopefully you've looked back at those notes, but just to touch on a couple important things. The first is the definition of an electric field. It's the force per unit charge experienced by a small positive test charge. And again, we know that positive part is important because fields are vectors. And when we're talking about vectors, the direction does matter. And so the vector for the electrical field points in the direction of the force on the positive charge. And when we're mathematically addressing force per unit charge, it's going to look like this, F over Q. And our units are newtons per coulomb, force per unit charge. Now we should also remember our Coulomb's law equation, and that's simply the magnitude of the electrostatic force between any two charges, and it's K, the electrostatic constant, times Q1, Q2, so the two charges, divided by the square of the distance between the two. And so again, this is one of our inverse square laws, so Q1, Q2, here's our R, and this gives us the electrostatic force of each charge on the other one. Now, if we combine these two into a super equation to represent electric field strength, we can take force, plug it in down here, and we see that the Q's disappear, cancel out, and so what we end up with is an expression for electric field strength, KQ over R squared. And this allows us to find the strength or the force per unit charge on a small positive test charge at any distance or in any area around some other charge that we might be looking at. Now, as we move on, we're going to start talking about energy and potential energy, and hopefully as we talk about this, you see some similarities, you see a lot of parallels between this and what you just learned related to gravitational energy and gravitational fields, because the two they're very, very similar both in concept and in the math associated with them. And it's because they're both fields, they're both force at a distance. And so when we're talking about electrical potential energy, this is the work it takes, or the change in energy, because remember that's what work is, change in energy, done moving a positive charge. Again, we're always just generalizing with a positive charge from a point of lower potential to a point of higher potential. And before we get too far, we're going to talk about this idea of electrical potential in a little bit, but it's essentially the energy, the change in energy from an infinite point away up to that point. And then also with this, because we're talking about positive charges, when we're talking about other positive charges, that's a high potential. It's like a hill if we're talking about gravity. And a negative charge is a low potential. And so to kind of, let's draw. Okay, so the top of our hill, or if we have a very high hill, that's like a large positive charge. If we have a negative charge, that's like a deep valley. The larger the negative charge, the deeper the valley. The larger the positive charge, the higher the hill. The greater the potential energy associated with it. And our units for potential energy are what we call volts. And 1 volt, 1 V, is equivalent to 1 joule per coulomb. If you kind of look at what that unit joule per coulomb is, it's energy per unit charge. It's how much energy does the test charge gain per unit charge. So energy per coulomb, or energy per charge. And our equation for electrical potential energy is KQ1, Q2 over R. So electrostatic force, KQ1, Q2 over R squared. Potential energy, it's just R. There's no R squared. So notice the similarities, but notice that they are two different equations. And then if we talk about just potential, potential is numerically equal to the work done. So again, we're talking about work, which means we're talking about change in energy. But here, when we're talking about electrical potential, we're talking about bringing some test charge from an infinite distance away, from infinity and beyond, to that point in that new field. And it's a scalar quantity, just like electrical potential energy, just like gravitational potential, just like gravitational potential energy. It doesn't matter how it gets there. The only thing that matters is the difference between the original location and the final location. And again, our units are volts or joules per coulomb, depending on what you prefer. The calculation, the equation for this, a long, needlessly complex equation to calculate the electrical potential for a point charge. We don't need to know it. All you need to know is that the equation for the electric field, or the electric potential rather, is kq over r. K is the constant, q is the charge that you're talking about, and r is the distance from that point charge. And so now we have electric field, we have electrical potential, we have electrical potential energy, three very similar concepts, but all unique and different in their own super. Now if we actually look at that field a little bit, let's say we have a positive test charge, and we know that the field is of course going to be acting away because that's the direction of the force on a positive test charge from our positive point here. And so our field is going to look like this. And again, the density, the line density at any given point in a field is a direct indicator of that field strength. And so you can see that in close, the lines are very densely compacted, but as we get further away, they get more spread out. They get less dense, which tells us that the field strength is smaller. Now with this, we have another aspect besides the electrical field, and it's what we call equipotential lines. And equipotential lines are simply lines that we're going to draw on here that are going to show areas where the potential, the electrical potential, is all the same. And if we draw one here, we're going to imagine that I can draw a perfect circle, and that this is a perfect circle. This green line is an equipotential line. Every point along this line, the electrical potential is exactly the same. And if we draw another line here, another circle there, the electrical potential along that circle, everywhere along that point, is exactly the same, but greater than this outer one. And if we draw one a little bit further away, the electrical potential on this line is a little bit smaller, but it's still there. It's still the same. So this line right here, all around it, the potential is the same, but smaller than this line. This line, it's all the same, but it's less than this interior line. It's all the same here. And we could do this as we get further and further out, and each line represents a place or a series of positions where the potential is the same. And as we get further out, that potential decreases. Now, it may not be clear on my diagram, but the relationship between the potential lines and the electric field lines is one in which the two exist at a 90-degree angle to each other. So the equipotential lines will always cross the electric field lines at a 90-degree angle. Okay, now the next part of this is kind of looking at the gradient, the field strength and the potential gradient. And we know that if we move a charged particle in a uniform electric field, and it's important to remember our point charges are not uniform, they're always changing, but if we look at a uniform electric field, as we move the charge some distance, we'll call delta x, the work done on the particle, the change in energy, is equal to the force times the change in the position. Remember, excuse me, wow. Work is equal to FD, force times distance. We can use this in a uniform field because in a uniform field the force will remain constant. The force F and the electric field are oppositely directed, so our force is equal to negative Q times the electric field. Our change in W is equal to Q delta V. And so if we plug F delta X in, we end up with, or excuse me, if we plug QE in for force, we get Q delta V is equal to negative Q E delta X. Okay, we set delta W equal to delta W, and then we plugged negative QE in here for F up here. When we simplify, the Q's cancel out, and we have yet another equation for electric field strength that is negative delta V, or negative change in voltage, divided by change in position. So electric field strength is the change in voltage divided by the distance moved in that field. Now this is just a nice little diagram to kind of show us the relationship between electrical potential and electrical field in a couple particular scenarios. Here we have two parallel plates. The electrical field strength between the two is uniform, but as we go from left to right, the electrical potential decreases. So a positive test charge here on the left side is going to have more potential energy than a positive test charge on the right side, and as it moves this direction, its potential energy is going to decrease, similar to a ball rolling down a hill. Now with our positive test charge, again, there's an exponential decrease in the electric field strength. It is a slightly different relationship, but still you see the potential as the positive charge moves away from the source or away from the charge, the electric potential decreases. With a negative charge, you should see it's pretty much the exact opposite. When we have a positive and a negative, it gets a little bit funky here. As we move from positive to negative, we see that the potential changes from positive to negative, and our electric field, actually, though, as we move from positive to negative, it gets weaker and weaker. In the middle, it's at its weakest. As we get closer to the other charge, though, we see it start to gain in. Then the next section here is potential due to one or more point charges. And really, when we're finding potential due to one or more point charges at any given point, it's simply, again, adding them all up using vectors. And so, if we have three charges, negative 6, 3 microcoulombs, positive 2 microcoulombs, we can find the electric field, and say we want to find it here. All we have to do is find the electric field, let's call this Q1, Q2, Q3. So we find the electric field for Q1. We find the electric field at some distance for Q2, D1, and we find the electric field at this distance, D3, for Q3, and then all we have to do is add them together. So similar to how we